Um, uh, Welcome everyone to another fun, super happy fun time with Musa and friends. We will be doing discrete mathematics as usual, and I hope you enjoyed today's lecture and you asked numerous questions. As always, I have a chat open in front of me if you have things you'd like to ask. Just some things I'd like to point out for today. Let's just begin and then I can point out as need be. Let me switch to a different set of slides. Let's go here. No, let's not do this one either. Apologies. I'm trying to make sure I pick a reasonable slide deck. Okay. So here I just want to show you this little diagram before we get started. Last week, or last lecture, and previous weeks, we talked about indirect reasoning, right? And we said, you know what, if you want to specify something, it's enough to know its relationships with everyone else, right? So, for example, there's a lot of proverbs in different cultures that say, tell me about a man's friends, and I'll tell you about the man. Right, you know, or tell me about a person's friend group, and I'll tell you about that person. If the person's always around bad people, then the person might be bad, right? And indirect reasoning says, hey, tell me about all the numbers x below z, and I'll tell you what z is. And so if we're given this equation that says, hey, everything x below z is precisely the same as x below 5, so I know that z equals 5. Right? That's how indirect reasoning works. Here we're saying to understand the pseudo complement, it's enough to understand its relationship to all other sets. And we're saying something is below the pseudo complement precisely when it complements A, right? When I have A and then I add some more pieces X, then I can get to B. Right? It's a complement that way. It complements, it helps get us to B. Okay, so we're starting at A and we can get to B by X. Okay, and so today we're doing the same thing. We're saying, hey, what's this weird division operation? And we're saying for any X, that X is going to be below the division operation precisely when I take R and I multiply it by X to get to S. Right. So this is that familiar integer division, right? You have three numbers, for example, R, X, and S. And you say, hey, how do I divide R by S? R divided by S is going to be the largest X, right? That makes this equation true, right? So it's the largest one that makes this true. So if I have something below R divided by X, then it's going to make the equation true. And if I have a solution X that makes the equation Rx included in S true, then I know X has to be less than the largest such solution, right? And so we've been calling these the characterization of these operations, okay? They solve these universal equations. So today we're going to look at another one like that, and today we're going to look at these divisions, which hopefully you've seen already by now. So they appeared in assignment 1, and then they appeared again in assignment 3, and now they're again in assignment 4, and now we're talking about them in lecture. So following the feedback, we're trying to reinforce things from different angles, so not leaving everything in the assignments. And with that in mind, homework 18 was just released, and homework 18 in particular is about relation algebraic proofs, which is to say it's just assignment 4. It's just assignment 4, but now we want you to think in particular that the symbols denote relations. Okay, so in assignment 4 we say, hey, these could be numbers, they could be sequences for concatenation, all right? Then we said, it might not be appropriate to treat these as sequences anymore, so we can treat them as matrices or relations, right? So we gave different interpretations for assignment 4. And in homework 18, we're saying, all right, here's a bunch of fill in the blanks just to get you comfortable, and you're welcome to treat these as relations, okay? So you can see how this we could have put it in assignment 4 using join and inclusion, but we're showing it to you as if it was relations, and you could prove it like this, or you could prove it much more compactly using just the abstract reasoning. Okay, so sometimes having just the minimal setting can be very efficient for proofs, whereas working with an interpretation can be quite messy. Lots of variables to worry about. Okay, so I hope that helps. Alrighty. So hopefully that's what we're doing there with homework 18 to reinforce assignment 4. Now there's some questions about the upcoming midterm. So let me just point that out. So here's what we're doing for the upcoming midterm. Today we're going to talk about relation algebraic proofs, which is homework 18 and assignment 4. All right. And it's going to be useful, going to the exam and to help you with assignment 4, but it will not be on midterm 5. Okay, so just to be clear, it's not going to be on midterm 5. Okay, so assignment 4 stuff, homework 18 stuff is not going to be on midterm 5. But assignment 4 does point out, hey, there is some stuff you want to do for midterm 5. Okay, so here's some stuff you would like to have done for midterm 5. So Risha asks, what does the semicolon do? So let's get back to the lecture at hand, and I would like to let you know that after yesterday's discussion, we've improved the reference sheet for this class. So in particular, on the last page, there's some examples and about what these operations mean and how you can think of them. And Risha was asking, what does the semicolon mean? And you can think of the semicolon as, and then this other thing. So just as in programming you write a semicolon to sequence programs. In English, you write a semicolon to sequence clauses of phrases. Likewise, we're going to use semicolon here to denote the composition of relations. Okay, Dux? Does that help, Risha and friends? Okay. So let's go back to the slides, and please continue asking questions. All right. So we've introduced composition, right? Semicolon, fat semicolon. You can think of that as multiplication. And if you think of it as multiplication, the next natural question is to ask, someone is saying, okay, all right, good question, Iman. All right, so Iman says, if we think of semicolon as sequencing, how do we think of division, right? So the way to think of division is, and if you decide to take Computer Science 3 EA3, you'll see this more in depth. But the way to think of division is as the weakest precondition to a program, right? So I'll come back to that later, but for now, I've given you some examples right here on division and where you have actually seen it. So we've already used division before secretly. So the subset relation is really a division. It's membership divided by itself. A while back and throughout chapter 15, you've seen these indirect reasoning rules, which say, hey, X is included in Y precisely when everything above Y is also above X, or everything below X is also below Y. And that's just saying, hey, the order is itself. When you divide it by itself, it's the same thing. So indirect reasoning from below and indirect reasoning from above. And here's some ways to read these things if you are so inclined. Okay, Dux. Good question, Iman. Tammy points out another thing in that fat semicolon relation composition is for functions, it becomes function composition. All right. But in general, when you think of a relation as for example, a database, so there's a lot of values that are being considered. then we're saying, hey, the input is you, and then I want, I'm going to query the database R, and I want some output X that's related to you. And for that particular X, I want to feed that one into the program S, and I want to get V out. Okay, so think I have two databases, and I have you as a student in the first database, and I want to consider all the information X from you, and I'm hoping one of those informations I can feed into the other database to get V out. Okay, so it's more general than function composition, and as you'll see in homework 18 and assignment 4, functions are special kinds of relations, and that's the topic of today. So excellent observation, Tammy and Eamon. So let's go back there. So if you think of composition as multiplication, the next question to ask is, what is division? And which is what we've asked since assignment 1 with regards to groups and monoids, right? And how we said, hey, implication is kind of like the division with respect to and, right? And so this is yet another one. And to help you remember all of these rules, we just squeezed the relevant stuff on division into this little corner of the cheat sheet. Okay, so pseudo complements are a kind of division. A difference is a kind of division, right? So we just squeeze the relevant properties here. So the Dedekind laws are here as well, and the other ones that you will see in assignment 4. Right? So just trying to squeeze a lot of stuff here, so it's easy for you to refer to. Likewise for all these names that you're going to encounter in homework 18 and assignment 4. So just a handy dandy reference, hopefully. Okay, so the division is the largest relation that allows us to solve these kind of equations. Okay, so we're saying, hey, I want to go from R to S. Sorry, I'm performing the operation R, right? So R takes me from A to B, but I really would like to get to C somehow. I know that A lets me go to C, and so the division says, okay, what if I start at C, for example, go back to A, and then from A go to B, right? So I'm trying to undo, okay? Or another way to think of it is to go from B to C. How do you go from B to C? First, go back via R to get to A. Now that you've gone back, so notice how R is under the division symbol. R is under it, so we're going backwards. We're trying to undo R, and that's what assignment 4 is about. It's undoability. So we want to go from B to C. So we walk backwards along R, and then we walk forwards along S. Okay, and we want the best way to walk backwards and then walk forwards, and that best way is going to be called R under S. Okay, dokes. Does that help? Okay. So just as we did for pseudo complement, we can look at this, look at its characterization, and then simplify it into a point-wise formula involving all these names, A and a quantifier. And then we can realize, wait a minute, we've already seen this kind of thing as a composition, right? There exists an A such that R converse is related to that A and S is related to that A. And so we can rewrite it this way. So this would be very helpful prep for the midterm to actually try to do this. Okay, dokes. All right. Are there any? Okay, I'm glad that makes sense. Yeah, please let me know when things make sense. Then I'm like, all right, that makes sense. I shouldn't keep talking about it. And if they don't make sense, please let me know and I'll talk about it more. All right. So here's an example of a relationship using division, right? So everybody called by Aus is a brother of Jun, right? Or initially, Aus called only brothers of Jun. So writing it this way can be a bit complex, right? You know, for every person that Aus called, that person is a brother of Jun. But then we can slowly rewrite it into this more compact thing, right? And I hope you'll see these definitions to be easier to formalize, and you can only do so really with practice, right? And so that's what I've tried to do by giving you these ways to read these relationships. Okay, so it's really with sufficient practice you can read these new formulae. Okay, ducks. And the slides have been posted, so I'll leave the other example alone. The plan today is to finish up with relations. So yesterday we began with the modal rule and Dedekind, and we hurried through it. And I said I'll come back to it. I don't want you guys to miss out because I'm in a rush. So we'll come back to it, and then we'll move on to combinatorial analysis. And this will be the end of the term, I suppose, right? When we wrap up with combinatorics, right? The theory of counting. How do you count? Does it count? If it counts, does it matter? Right. So there's a lot of puns involving counting. So we'll go there. First, I would like to show you this Nido slide. Oh, minimize that. Minimize. No. Okay. All right, that didn't help either. Okay, so I just want to show you this Nido slide right here, which has all the examples as well. They're also shown on the class cheat sheet. But here's something I want you to pay attention to. Notice whenever we have a formula involving for all or exists, we have those trading rules that let us move the range into the body. So here, this is X is related to U is a constraint on X, and then the body is X is related to V, right? In comparison, this is just an implication that has no range. So we could rephrase them as follows. So now there are no constraints on the variables. Everything is inside the body, right? So occasionally when you use these formulae, hint, hint, wink, wink, right? When you use these, you might need to invoke trading, okay? So it's just things to be on the lookout. So you've probably already encountered this already in some of the homeworks. So I just want to really point that out, okay? So if you use the rule in this form, if the rule is given to you in this form, and you want to use it as if it was an implication, you will need to invoke trading. Okay, ducks? All right. Okay. So this is a slide, attention, this is a slide that you should mostly be familiar with going to midterm 5. So let's just look at it briefly. You should know what a relation is. You should have an idea of what cup and cap are, what intersection and union are. You should have an idea of what the empty and the universal relation are. You should have an idea of what complement is, okay? You should have an idea of what pseudo-complement is, right? And these are mostly summarized already in the cheat sheet for you. You should definitely know how composition works. You should know the definition of composition. You should know that composition is, well, like multiplication, it's associative, monotonic, and has an identity. Some useful properties, right? You should be aware of converse, which is mentioned to you in assignment 4, that, hey, converse is a thing you should know for midterm 5. You should be aware, you should be able to prove this property, for example, right? So we proved it in lecture on Tuesday, I think. So you should be able to prove that. You should be able to prove this, right? So some of these simple properties, good practice. Here's some more advanced properties, right? If you have the time, try to prove these. Good practice to help you understand how composition works, how intersection works, how converse works, how division works. So I think try to prove these as good practice for midterm 5. So this slide, try to be familiar with the content of the slide for midterm 5. All right, and I hope that really helps, right, to pointing this out. What's the name of that smaller arrow? What's the name of that smaller arrow? Oh, I have a lot of arrows here. So this is for relations, and this one is called the pseudo-complement. And it's the pseudo-complement is another kind of division. So here we have these division operations, and one of them is the pseudo-complement. Okay. So the pseudo complement is when you try to divide, but your multiplication operation is conjunction or meet or intersection. Semi-complement is when you try to divide, but your operation is union or maximum, right? So, or join. Does that help, Eamon? Okay. So let's move on then. So here's an example. Last time we showed monotonicity from subdistributivity. If instead we start off with monotonicity, right? We say, hey, multiplication preserves order, then we can show really easily that it subdistributes over meet. Right? We start off here. We double up the equation. Here it is once. We double it up because meet is idempotent. Remember, P and P is P, right? Then we say, oh, hey, meet composition is monotonic, and I know R and S is contained in just S, right here. R and S is contained in just S. And then likewise, R and S is contained in just R. This is the weakening rules. All right, so just to bring them up again. Okay. So it's these weakening rules that you've seen before. A and B is contained in A, and A is contained in A or B. These 376 and friends, right? Rules. Okay, ducks. All right, excellent. Please continue to ask more questions. So the proof is really simple. Now here's a challenge. Right? Here's a challenge. If you have the time and energy and mental capacity, prove this rule using for all and exists. So start off with replacing this by a for all, then replacing this one by a for an exists, replacing that by an exists, replacing that by an exists, putting in all the points. So try doing that and see if it falls off the page. So that's a lot of fun, I guess. The neat thing about these relation algebraic proofs, it's so small and cute, is that so we've given you the general setting under this. I've just called it residuals and division. But here's the theorem, right? Subdistributivity over meet, and the proof for this one is the exact same proof that we saw right here. It's the same proof. Okay, so we're using intersection and union to just continue with that set theory trend, and this is what's normally used. But the abstract setting, it's still the same proof. So these relation algebraic proofs are just the abstract proofs you're familiar with from assignment 3 and assignment 4. Okay. So and they're much easier because they hide away all the fires. So that's nice. Okay, next. So yesterday we were here at converse as over approximation of inverse, and I'll just quickly go over it till we got to Dedekind. All right. So you have Q and you're doing Q and then you're doing R. Let me change the arrows. You're gonna go Q. Oh, all right. Q will get you all the way to B, and then to get to C you use R. And at the same time, you also you want S to be true. So you're trying to do multiple things at the same time. Then you can forget about the relationship with S. Right? You duplicate it, but forget a little bit to get to the other side. Right? So the idea is it's like I have Q times R intersect S, and this is contained, right? I'm going to divide essentially by Q inverse. Okay, so you may have seen this formula. You may be more comfortable seeing it using division, right? So I have A divided by B, okay, and then I want to take the minimum with C. So I have 3 numbers, and I'm saying I have A divided by B minimum C, and you can see that as saying, oh, I'll take the minimum of A times C, and then I'll divide by A. Okay, so I can pull out the division by A, of course, by making the other argument a multiple of A, right? And then A divided by the multiple cancels out, and then I can get back here. Okay, for numbers, multiplication is cancelable, right? when you have a times x and a times y, you can cancel out the a's for non-zero a to get x equals y. But in general, multiplication might not be cancelable, right? So if your multiplication is and you say p and false equals q and false, well, that's true. It's always going to be true because p and false is false and q and false is false and false equals false. But p and false equals q and false does not mean you can cancel out false to get p equals q, because p equals q is not always true. There are choices for p and q that are different. In particular, true and false, right? So these are inclusions instead of equalities, because in general, multiplication or composition is not cancelable. You can't get rid of it, right? This is the cancellation laws you've seen before for multiplication and addition back in the first few weeks. That's what I mean when I say cancellation, okay? And so that's how we get these ones, right? We think of the converse as an approximate inverse, right? It's like I have q times r, minimum with s, and then I pull out q, I pull it this way, so I pull it all the way out. So when I multiply q times r, and then when I multiply q times q inverse, they almost cancel, not really, but almost, and that's how I get this rule. Okay, and it's a very useful rule to have when you're doing relational algebraic proofs without quantifiers. So I just want to point that out, like 332 or 372 or 364. So there's some of these nameless rules all over the place. So here's this one. 362 is a useful rule to know, right? We've mentioned for you 332 before. And today we're mentioning this modal rule. Modal means to change the shape or the mode, and here we're changing the shape from here to this new shape. Right? The name is not very clever, I guess. It's a very obvious name. I have one shape and I've changed it to another shape. Duh. But it is a very helpful rule. So I just want to spend some time on it. And of course, instead of pulling out q, I can pull out r. I pull out r to the other side, and then I stick an r in converse. Okay. So we talked about these yesterday, and then we said, hey, recall that inclusion can be thought of as meets, and so you can always take these inclusions and turn them into equalities. Okay. So as we said before, you have this induced definition, right? You can always take inclusions and turn them into meets. Right, or joins, and so you can turn these into equalities. Then yesterday we said, hey, what if you do both factorizations at the same time? And that's called the Dedekind rule, right? So it's like doing modal rules together, right? I can pull out q, or I can pull out r, or I can pull out both, right? And I get this interesting shape. Okay, and these formulae might be a bit tricky, and they're a bit hard to remember. And again, like everything else, with enough practice, doing the homeworks, you'll use the rules enough times that you'll be like, I know where it goes, I know where that symbol goes. For now, they might appear a bit daunting. Okay, so as we try to show over here, you can always think of a converse as an inverse operation, and more accurately, you can use these divisions to get familiar rules. And incidentally, if you think of composition as multiplication, these become equalities, right? A divided by B minimum with C is equal to A divided by the minimum of B with A times C, okay? And this works because multiplication distributes over minimum and maximum. And so you can prove these rules right there. So that's pretty neat. And tropical mathematics is summarized right here really quickly for you. Super tersely. This is chapter 15. So tersely. So that's the numerous ways you can, as before, you can think of it as a triangle, and then you forget about a common relationship, right? Another way to think about it by using the an intersection is to say, hey, I have the two triangles. right? But now I remember the relationship, right? So before I forgot about B, now I remember the shared B. Okay. So different people understand these formulae by practice. Some people just get it because it looks like arithmetic. Other people use diagrams, right? And different people learn differently. So hopefully showing you these just communicates different ways to learn. Okay. So here's an example that I tried to get you to yesterday, but I rushed over really quickly. So let's talk about it right now. We've proven before, and we talked about it yesterday, that if you have a relation that's reflexive and transitive, then it's necessarily idempotent. Okay, and idempotent just means doing it multiple times doesn't matter, right? Doing it once versus doing it 100 times, same effect. Okay, it's going to have the same effect. Okay, so we've shown this before. And it's quite simple. So I hope as extra practice for the midterm, try to be you should be able to prove this comfortably, right? You know, what does idempotent mean? What does transitive mean? What does reflexive mean? It means these weird equations. Okay, what does this curly less than or equal to mean? What does this fat semicolon mean? Let me simplify and get back to for alls and exist everywhere and try to work with that mess. Okay. So here's a proof that if it's symmetric and transitive, it's also idempotent. Now this proof is hard to do without Dedekind or without the modal rules, right? So you have to unpack these definitions using for alls and exists, and you can prove it. Or you can say, hey, let me start off. Let me duplicate what I know because it's idempotent. R is the same as R intersect R. And then I can bring in an identity. And now I have a composition and a meet, so I can use modal rules. And modal rules will let me factor out R. So I take this R and I pull it out. And what's left is the identity is still there. That R is still there. But because I pulled out this R, I stick an R converse right here. Okay. Now that I've done this, and the reason I want to do this is because transitivity tells us R times R is contained in R, right? So we're working up to that, and symmetry tells us converse does not matter. Okay, so we've made it here, right? We want to get to using this rule, so we'll drop the identity, right? Using monotonicity and weakening. So now we're here. And symmetry tells us converse doesn't matter, so we get rid of that. And now we can finally apply transitivity to get R times R is contained in R. Okay, so this hinges on using the modal rule. Without the modal rule, we would have to resort to using these definitions. Okay, so that's the benefit of using these approximate inverse rules, right? I can factor out Q. And I stick a Q inverse over there, but the factorization is an approximate. It's not equal. Right? And this is very, very helpful to have around. Okay. Okay. So these properties, I've shown them before, and they're in the cheat sheet. But I just want to talk about them for the next slide we're going to get into. These operations have particular kinds of arrows to abbreviate what they mean. All right. So let's go. So univalent means same input, same output. Total means always terminates for any input. There's always an output. For any input, there is an output. Injective means if two inputs go to the same output, then they must have been the same, right? So different stuff goes to different things. Okay, surjective means every output comes from an input. Okay, and these interpretations are also summarized for you in the cheat sheet. Okay, ducks. So here's an example. Suppose F is univalent. So same inputs go to same outputs. Then we're saying, hey, F actually distributes on the nose. It's an equality. It's not a less than or equal to, it's an equality, right? So before we said it's a less than or equal to for composition over meets, but we're saying not if the first one is univalent. And here's a really, really ugly proof. And it's so hard to read, and it's so long. If I have to zoom it for you, it's just a mess. But if you use the higher order language of just compositions, modal rules, meets, identities, it suddenly becomes a 3-step proof. So that's cute. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is about 12 steps, and now it's 3. So you divide by 3. It's a third of the effort if you use a relation algebraic proof style. All right. So this is just using that abstract notation from assignment 3 and assignment 4. Right. So it becomes much easier. 3 steps. Okay. Here it's so long and so long. Right. So wide, so long. Here it's so cute. And it's really, there's not much to do. You have these things, and you have some properties right here, and you only know some properties about meat and composition. So there's not much to do, and so the proof suggests itself. Right? When there aren't many things you can try, you say, all right, there's only a few things I can try, and then suddenly you can find the proof easier this way. Okay. All right. The next thing I want to talk about, Tammy pointed out earlier about functions or maps, right? When we think of an inverse, it actually happens to be a converse for bijective maps, right? So for relations that are total, univalent, surjective, and bijective, if they satisfy all these cool properties we're interested in, then inverse and converse are the same thing. Okay, and you've seen these for matrices before. These are permutations of the identity matrix. So take the identity matrix, which is just zeros everywhere and ones down the diagonal, and then just shuffle the columns around, and that's a permutation. Or if you think of a graph with a bunch of circles, right? So here's one circle, and if there's other circles around or cycles, then that one's also a bijective mapping. Okay, so this idea of converse as generalizing inverse, right, is found right here, and you'll prove some stuff like that in assignment 4, as summarized here as well, right here. So here's situations where converse actually does behave as an inverse. And there are many more situations, and we're not going to mention them to avoid overburdening you with a lot of stuff. Okay, ducks? All right. So I'll leave this proof to you. Hopefully you'll be able to read it and understand what's going on. If not, please ask for help on course help. But trying to find out what's going on in this step, right? What's going on in this step, right? There's nothing really new here, but I would like you to practice reading this on your own, and perhaps it will bring up things you're not comfortable with, and then you can ask questions. Okay. There's these 4 properties I mentioned earlier, being total, being univalent, surjective, and bijective. And then when you mix some of them, you get mappings and isos. So they have a particular notation, right? So this is an ISO standard called Z, right? Z notation, and we're really so this is from them. This is that's why this is their notation. Okay, so the stuff you're learning in this class is actually according to this ISO standard, right? So and in that standard they use these arrows to denote particular properties. Univalent relations are also called partial functions, and they're an arrow with a dot in the with a line in the middle, right? Total functions, that is total and univalent relations, are a full normal arrow as you've seen them, right? Arrows with a hook like this are known as total injections, and as usual, you use a line through it to make it partial, right? And so we just want to show you that, hey, this ISO standard used for specifying programs for formally proving them correct. You guys you're all learning this stuff, and if you decided to learn more about using Z or take other classes at McMaster that make use of Z, there's a few other classes. You are well equipped to make use of that formalism. Okay. And so this is again from them. This is their notation, right? So instead of equivalence, they use the double-headed arrow. Okay. They use a tilde up here to mean converse. Okay. They use circle instead of fat semicolon. But there's a few reasonable rules, right? If f is a partial function, so f is univalent, then you have this property, right? That the range of f, all right, the identity on the range of f, it can be obtained by doing f followed by f converse, right? So there's a lot of stuff. You'll be able to read it, right? If you decide to pick up any book on using Z, or work with the ISO Z standard, or take other classes that involve it. So just thought this was a good time to mention this. Okay. And they have interesting names for these, and let's actually count some of these names, right? Count how many functions, how many injections, right? Because the idea is to move into combinatorics next, so we'll begin there. Okay. So I'll leave this reference slide for you later. Okay. These properties are also listed on the cheat sheet, so I won't spend time on them. All right. So let's count how many of these sets are there. So if you recall back last week, I said, hey, if you have two sets and you want to count how many elements are in the sets, then really it's going to be all the elements here times all the elements here. All right. Just making sure. Regarding questions, please continue asking. Okay. We said to count the power set, you just do 2 to the power of, because everything for every element can either be in the set or not in the subset. In or not. In or not. There's 2 options, and if you have n many elements, it's going to be 2 to the power of n. Okay. And we're going to talk about why it's 2 to the power of n and how you can prove it. Right? We've mentioned before combinatorics, and we said n choose r, and we said the permutations of n and r are permutations of n. Right? And we can, now that we have sets and cardinality, we can prove that these numbers before, which we claimed denoted the number of permutations in a line, or the number of subsets S of size A. Well, now we can prove it. All right. And now that we have the language for it. Okay. So this is chapter 16. And I'll just go over some of these really quickly, and then we'll come back to them as needed. If you have a bunch of sets S and they're disjoint, so remember the principle of inclusion, exclusion, or if you like, a range split, right? 816, 817, right? If you union a bunch of sets, that's just like and you want to find the size, that's just adding up all the sizes because they're disjoint. There's no commonality, and so you just add them up, right? So this is, you've seen it before in this shape, right? So to count how many things are in S and T, I count how many are in S, how many are in T, and I get rid of all the duplicates. I overcounted in S and in T, so let me get rid of the overcounting once. All right. Product, right? If I'm doing something, if I have SO many possibilities for the first one, S1 for the next one, all the way to the end, I multiply, right, to get the total, right? We'll get into these in time. I wanted to show you these. And then the last one right here says, if I have a bijective mapping between A and B, then in fact, the sizes of A and B are the same, right? They are equinumerous sets. They have the same amount of things, right? So what does this mean, right? It means every A value can be associated to a B value. That's what total means. Total means every A goes to a B. Okay, great. Then univalent says every A goes to at most one B. Okay, so now we know the number of A's has to be less than the number of B's, because every A goes to a B and every A goes to at most one B. Okay, so that's A is at most B. Great. Then we said it's surjective. So every B has to be hit by some A, right? And then finally, we said it's injective as well, right? And so different B's have to come from different A's. And so that gives us that they must be equal. The number of A's and B's has to be equal, okay? We'll get to formal proofs, but just want to show you some of these today, all right? Okay. So we've talked about pairs, relations, partial functions, right? So partial functions are just univalent relations, right? So let's look into that slightly a bit more. So I think it was, should have just written it down. I forgot which homework it was, but we had a homework where we had you guys working on factorial and on permutation. And we said, hey, if you have n many things and you want to be able to, you have n many people and you want these people to stand in a line, right? You know, tallest to shortest, shortest to tallest, boy, girl, whatever. I want to arrange people according to their height, right? How many ways can you arrange n many people, right? That's the permutation of a set of n elements. And we just told you, we tried to argue in the prose that if you have n many people, there are n factorial ways to arrange them, okay? And using that as our basic definition, we tried to talk more about n factorial, okay? But a permutation, we said not a few slides ago, is a bijective mapping, right? And so we can count how many bijective mappings are there, right? And so let's look at the finite case, right? So we defined P to talk about the number of R permutations of a set of n elements. And we said it's this zany division right here. And we said the zany division is always going to be an integer, and we argued for it in that homework. And I presented it to you this way because back then we didn't have division in our hands. And so we worked with this formulation for a while. Now that we have quantifiers, we can express it as a product of subtractions, or as a product like this, where the subtraction moves to the range instead of the body, okay? And now we can rephrase our claim as this theorem, right? The number of R permutations of a set of size n equals P n R, okay? So Eamon asks, what are we talking about? What's going on? All right, so that's a good question. I guess I lost some of you. So Eamon, we wrapped up relations. We said, hey, before we wrap up, here's some useful rules called Modal and Dedekind. They justify why we call converse an approximate inverse, right? They justify that treatment of converse. Then we said, all right, we're done with that. Let's look at how many. Let's look at the properties of these arrows. All right. The ISO Z standard gives them a special notation, and then we said, okay, now that we have that notation, how many possible elements are in these sets? And that's where we are now. And then, Eamon, we said, hey, we're counting how many possible bijections there are, how many possible injections there are, and why are we interested in these counting? Because a while back we gave you guys a homework on permutations, and we made these outlandish claims that n factorial is the number of ways to arrange n people in a line, and now that we have the mathematical tools to talk about it, we can formalize it. What is a group of people? That's a set. When we say a group of n people, that's a set of size n. And then when we say, what does it mean to arrange them in a line? That's a permutation. And a permutation uses these funky arrows that we introduced a moment ago. All right. So and that's where we are right now. Right? Does that help, Eamon? All right. Okay, so we're trying to count how many possible things there are, and before we did it informally because we didn't have quantifiers or sets or cardinality, and now we do, and so that's what we're just trying to do. Okay, but I've run out of time, and it seems I've confused some of you more than I wanted. I was trying to get here, so I'm happy to make these recaps. Please always ask. Last thing I want is for you guys to be lost. So we'll stop here. We'll stop here today. and we'll pick up tomorrow at this slide. All right. I hope you're all getting ready, and I just want to remind you to look at this particular slide. Where is it? Right here. Right here. This one, just for the test. So please try to understand some of the stuff on this slide. Try to prove some of these theorems if you have time. It will be good practice. You know, what does this fat semicolon mean? What does this thing mean? Where's all the for alls and the exist? Let me unfold it, and then your page will fall off. It's so long, and you know it will be extra practice for you. Okay. I wish everyone the best, and all the best with the midterm. And I'll be here in case anyone else has any questions.